The last discrete distribution we will talk about in this lecture is the Poisson distribution. Okay, first thing first, this is not Poisson distribution. Okay, this is the name of a French mathematician, and as many French names, this is read or this is pronounced quite different to what it looks. It's Poisson. So the parameter is lambda, and let's look at the definition or the interpretation. Let's say the Poisson distribution represents the number of occurrences of a completely random event within a given time interval. What does this mean? Completely random event. We will talk about this. The only information given to us besides this nature, completely random nature, is the mean number of events. The mean number of events is assumed to be known, which is lambda. Okay, so we are given a time interval. Okay, the length is irrelevant here. Um, but we just know that events, a certain type of event, whatever that is, okay, let's say the bus coming to a stop, or let's say an earthquake happening in a specific point in a specific location, or a lightning hitting a specific uh, location, let's say. Um, so you just know the mean number of such events occurring in a given time interval, and you just know the nature of the event is completely random. Now we are going to model this by discretizing the time interval into n slots. So this is my time interval, okay, and I'm going to divide this into n slots, n times slots, equal slots. But for a practical, for the practical purposes, this n will be a large number, and later on we will take the limit to infinity. Now, a completely random event can be characterized by the following assumptions. We will assume each of these slots, 1 up to n, is independent of others. That means if an event occurs here, that will not affect the occurrence of an event in this slot. Okay, you do not decide on whether an event occurs in a slot by looking at the nearby slots. Okay, you will not say, okay, an event occurred here, maybe I'm just going to give it at some distance, I will not let an event occurring here. Okay, so that's disallowed. Each slot is independent, and they have the same probability of having one event. And that is, well, if you model that with p, okay, on the average you see um, each slot will have on the average p events as its mean value. So when you multiply that with n, we have n slots, you'll have in total n times p events, which should be equal to lambda. So that gives us the value of the p parameter as lambda divided by n. Okay, and finally we will assume that each slot is so small, meaning that n is so large that the probability of two or more events occurring in the same slot is negligible. Okay, the slot is so small that we allow only one event or none in one slot. So what does this mean? The probability of an event in a slot is p, and the probability of more than one event is practically zero, which means the probability of zero events in a slot is 1 minus p. So each slot here is a Bernoulli trial, a Bernoulli p trial. And the number of total events is what? I have n Bernoulli trials here, Bernoulli p trials. And as I said, they are independent, okay? And therefore, the number of total events in this entire interval is the sum of each of these Bernoulli trials. Okay, the sum of n independent Bernoulli P trials. But we know what this is. That's a binomial NP random variable.